Welcome to my TED Talk. The first thing we're going to talk about today is angle pair relationships. What does that mean? Well, before we can even talk about that, we need to think about something that we haven't really seen yet, and I need to talk about it now, which is the idea of congruency. So here we have two little triangles right there. I'm going to call the triangle on the left A, and the triangle on the B over here on the left. Now, if I wanted to show that these two triangles have the same measurements on every single side, what I would need is a ruler. I have to measure out the leg of the longest side on this one. Let's say it's approximately 10 centimeters. And I do the same thing for this triangle all the way over here. Let's go ahead and say, yeah, it looks like 10 centimeters. And if I did the same thing for this side, it looks like 7 centimeters. And what we would find is that this side over here is also 7 centimeters. And then this triangle side up here looks like about, once again, 7 centimeters. And what we would find is this triangle over here has a side of 7 centimeters. And the reason why they would be the same is because they're both traced out versions of this green triangle that I have right here. Now notice that when I trace this green triangle, it doesn't actually change the shape of the triangle itself. When I say that, this triangle has the exact same shape and size. It doesn't matter if I flip it around like this, which we could learn to call a reflection transformation by flipping it around like this. This green triangle does not change size. It does not stretch or shrink if I rotate it around. It always stays the exact same size. If I go ahead and put it over triangle B, it'll still be the same size if I rotate it and align it with triangle A. Even if I move it back and forth, we would see that the side lengths do not change at all. So our transformations that we've learned in chapter 3 or 4 or 5 or 6, I don't remember. Our transformations are called congruency transformations. Congruency because it doesn't change the size of the thing that you're kind of transforming in the first place. That's this new thing we're going to talk about, congruency. When two things are congruent, they are the same size and the same shape. However, a key thing I want to point out is that congruency does not mean equal. Let me go ahead and show you a little bit more what that means. Congruency has its own little math emoji. It is an equal sign with a little tilde on top of it, a little squiggly right there. Because that's saying like, yeah, sure, these two have the same measurements, but at the same time, there's something a little bit different about what we're calling these things. For example, triangle A on the left over here is not the exact same triangle as triangle B. They're in two different spots on this piece of paper. They're in two different orientations, and they're not physically drawn on these same spots. So in order to kind of describe what's happening here, in order to kind of say that these two triangles have the same measurements but are two entirely different things, kind of like how twins, they look the same, sometimes sound the same, maybe even behave the same. They are two entirely different people. And so we would call them congruent. Same size and same shape. Here's another analogy. Here, I have one singular triangle that you can see looking face down onto the camera with the piece of paper here. But if I go ahead and do this, now this triangle over here, overlapping triangle A, is no longer the exact same thing that I have over here in triangle B. These two are different things entirely. They may have the same measurements, but they are not the exact same thing. These triangles are congruent. They're congruent no matter where I do, no matter where I move them, flip them, rotate them. These two things are congruent until, take a look at this. They're still congruent. They're still congruent. They're still congruent. But once I overlap them, once you can't even tell that there were two triangles, now you can say these two triangles are equal. They are the exact same thing. But split them apart, now they are congruent. And that's going to lead us into the next kind of step for talking about angle pair relationships. So let me go ahead and, like I said, it doesn't matter if we rotate, translate, or reflect this triangle. All of these side lengths are going to be the same. Similarly, all of these angle measurements are going to be the same. So this angle is always going to have the same measurement. Doesn't matter if I move it over here, turn it around, upside down. This angle will always have the same measurements. Same thing here. This angle will always have the same measurements after a congruency transformation. Let me go ahead and show you something pretty neat. So I'm going to go ahead and do is I'm going to align my little triangle right here, and I'm going to draw a line going off like this. And while we're at it, I'm going to go ahead and highlight this line over here as well. What I've gone ahead and done here is done my best to construct an angle. So here we have an angle that we created from drawing part of this triangle over here. And what I'm going to go ahead and do is I'm going to go ahead and extend this side length so that it's no longer just the side of a triangle. It is now an entire line that goes off like this. Now, as we mentioned, this angle right here, that I'm going to highlight with a little arc, is going to go ahead and match the angle of this green triangle right here. Now, what I'm going to go ahead and do is I'm going to move this green triangle along this new line that I've drawn. I'm not going to rotate it. I'm not going to reflect it. All I'm going to do is translate it. I'm going to translate this thing, and it's going to move slowly, slowly along that line, and I'm not going to rotate it in the slightest. Just keep it moving, choo-choo. And then we're going to have something that looks like this. And I'm going to go ahead and highlight this line right here. Now, what the heck did I just do? Because I didn't rotate around this triangle, this line segment right here, that I'm going to go ahead and title A and B. So if I want to talk about this line segment up here, I'm going to call that side AB, or segment AB. And this line segment down here, then I'm going to go ahead and call segment B, no, DC. DC over here. The line that starts with the letter D and ends with the letter C. Because I didn't rotate around this triangle when I was moving it along that line, these two segments, A, B, and DC, they're going to end up being parallel. Now, we can prove that a different class on a different day, but it's enough to just say that these two lines are parallel. And to say that they're parallel in geometry, we have these little arrows that go across the line segment like this. Now I'm going to go ahead and just extend this line. I'm going to do my best because you can see angles that I cannot because I'm stuck in my seat. And what we've gone ahead and done is we have drawn two parallel lines. And one thing we've kind of talked about is that this angle right here, angle ADC, is going to be congruent to this one all the way up here, because congruency transformations do not change the green triangle. And so just by moving it across, we've gone ahead and introduced our first ever angle pair relationship. This angle that I'm going to highlight in orange will be congruent to this angle all the way up here. They are the same size and the same angle measurement, but they're two completely different things. This angle is all the way up here, and it makes up the segment AB. This bottom angle is all the way down here, and it makes up the segment DC. These two angles are congruent. And so in geometry, to say that these two angles are congruent, what I'm going to go ahead and say is, or write, is a little tick mark right there. So this angle over here has the same measurement as this one down here. They are congruent. These angles, they are called corresponding angles. And this is a vocabulary term that it's very important for you to understand. So if this angle measure right here was 63 degrees, then I know that this angle down here is going to be 63 degrees. Next, let's talk about our other angle pair relationships. Let me go ahead and now, instead of translating, I'm going to go ahead and use my other transformation, rotations. So if I go ahead and rotate this triangle around, here we go, swivel, 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 swivel. One thing we're going to find is that, hey, look at that. This triangle lines up pretty well, or at least this angle does. This angle lines up pretty well with this angle on the opposite side of this intersection point with the orange angle. Isn't that a pretty neat coincidence? Let's go ahead and give that a name. Let's see, this is an intersection point, and so we have these two angles going across. And I'm going to tell you right now, this angle is going to be congruent to the orange angle. Let me go ahead and highlight this one in green. So corresponding angles, let's go ahead and just say those were two orange angles. This new angle pair relationship that we've got going on will have a new name, vertical angles. Another old-fashioned term for these is angles across an intersection point, or angles across a vertex. That's where this vertical comes from. Not vertical as in going straight up and down, vertical as in the vertex, a point where two lines intersect. So vertical angles is when you have two angles directly across from each other, directly across from an intersection point. These are demonstrated with the green and orange colors, whereas corresponding is just two orange angles. So like I'm guessing you can figure out this angle down here is also going to be congruent to the orange angles. Two orange angles are corresponding, a green and a orange are vertical. Vertical angles are congruent. So if I know that this angle over here is 63 degrees, then I already know that this orange one across from it is going to be 63 degrees also. And this green angle over here will be congruent to this other green angle over here because those are corresponding. But hey, check this out. We have this green angle and this orange angle. I'm going to highlight one more thing, which is the entire inside region of the parallel lines. And here we're going to finally learn about one of the most important angle pair relationships that you can talk about in geometry, because it's so useful and comes up a lot in IM2. This angle over here that I'm going to go ahead and call, what should we call this? Let's call it angle W. Angle W in green. And this angle I'm going to call angle, let's call it angle T. I hope that's visible. Angle W, angle T. These two angles are on the inside of these two parallel lines. So if this entire region was inside the parallel lines, then everything out here is on the exterior or outside of these two parallel lines. And you can't see that on the screen. But now you can, exterior. And this line going across the first and bottom, the top and bottom parallel lines, this line has a special name. It is called a transversal. This is a transversal line. It has the prefix trans. I'm sure if you live in a home where you have one parent speaking a language and another parent speaking a separate language, I'm sure you've had to translate between those two languages. Translate. One example could be translating from Spanish all the way to English and vice versa. If you are translating between these two languages, you're taking a message from one across the other. And so a transversal line travels across two parallel lines. And notice this green line, this green angle W, is on a different side of this orange angle T. So if we were to say that this transversal can be split in two pieces, let's go ahead and just say that this line has a left half going off over here, where I've written the words corresponding angles, and a right half going all the way to the bottom right of the screen, where I've written the words inside and exterior down here. So this transversal has a left half, and it has a right half. These two angles are congruent. They are on the inside of these two parallel lines, and the lights went out, so I have to go stand up and wave my hands around like some kind of freaking... Come on, there we go. And what was I even talking about? I have no idea. These are called alternate interior angles because they are in the inside of these two parallel lines, and they are alternate sides of the transversal. The green W angle is on the left half of the transversal. The orange T angle is on the right half of the transversal. And that is the next angle pair relationship that we're going to talk about. Angle pair relationships are congruent. What does congruent mean? They are the same size and same shape, but they are entirely two different things. But how can we use that to solve our homework problems? If I go ahead and give you an equation and a drawing that look like this, part of what I'm going to expect you to be able to do in order for you to be prepared for IM2 is first, know your vocabulary. I'm going to ask you, hey, if I give you an angle all the way up here, I'm going to label that with a circle with a line through it. That's a new symbol that we used that's different from the angle symbol. This symbol right there is called theta, but we just call it the angle symbol when you get to IM2. If I go ahead and give you this angle right here and this other angle down here, I'm going to ask you and expect that you know that these two are corresponding angles. If I instead give you something that looks like this, let's go ahead and write down a x plus 3 and then 2x. I'm going to ask you to draw or create an equation because in geometry we have all these nice geometric drawings, these parallel lines, these cute little math emojis, but what is the point of any of this? Why are we doing this? If I give you a drawing that looks like this, x plus 3 and then a 2x down here with this intersection down there, and I'm going to ask you to solve this, what do I mean? What do I want you to do? What am I really trying to ask? One, if you know your vocab and you know your angle pair relationships, you know that this angle up here is congruent to this angle down here. And if I ask you to solve this problem, what I want you to know is that, hey, these two angles have the same measurement. They are congruent. They are the same size and same shape. So I can set them equal to each other in an equation. And then from here, this is what you solve. This is what you want. In geometry, everything we are trying to do is turn this picture into an equation. Once we've done that, we don't even need the picture anymore. We just solved this. We have decomposed this entire thing into one equation. And I know you know how to solve this equation. Let's go ahead and take a look. 2x equals x plus 3 was my first step to solve this equation. My first step, I'm going to subtract an x from both sides. I have two x's, so subtract 1. I will have one singular x, both sides of these equations. And then from here I can easily see that x is equal to 3. The only new thing you're learning in this section is how to turn this picture into an equation using your vocab. You already know how to do this. This is easy for you. So on the handouts that I'm going to give you, I'm going to expect you to label what this angle pair relationship is. So in this case, this will be corresponding. And then I want you to write an equation. I might ask you to solve it too, or just write it. I don't know. I haven't decided this yet. I'm doing this in the classroom at 10 p.m. and my computer's going to die. So that's it for Module 1.